Hi, this is Mrs. LaBarbera. This is AP Physics Chapter 12, Gravitation Video 6. Today's topics are spherical mass, apparent weight, and black holes. The objectives are: know the statement, the gravitational interaction between two spherically symmetric mass distribution is the same as though all the mass of each were concentrated at its center, can be proved. Know that when a point mass m is inside a uniform spherical shell of mass big M, the potential energy is the same no matter where inside the shell the point mass is located. The gravitational force between the shell and the point mass is zero. Know what black holes are. Know what an event horizon is. Understand apparent weight is different from true weight due to Earth's rotation. Be able to calculate Schwarzschild Radius. A point mass outside a spherical shell. Consider the interaction of point mass m with a thin spherical shell with a total mass capital M. We can show that when m is outside the sphere, the potential energy associated with this gravitational interaction is the same as though m, the capital M, the shells m, were all concentrated at the center of the sphere. We can show by breaking this shell into different rings. Furthermore, we can break the ring into different masses. Then first we calculate each little mi and the point mass, the potential energy. We add all the potential energy together for the ring. Then we add all the potential energy of the ring together. And this is the result we have. So any spherically symmetrical mass distribution can be thought of a combination of concentric spherical shells. So again, for a solid mass, we can break the solid mass into many different shells. So by adding all the forces of the shell, we can prove that gravitational interaction between any spherically symmetric mass distribution and the point mass is the same as though all the mass of the spherically symmetric distribution were concentrated at its center. Furthermore, for any gravitational calculations, so any spherically symmetric mass distribution can be treated as a concentrated point mass at its center. So when a point mass is inside a thin spherical shell with total mass m, we can show the potential energy associated with this gravitational interaction is constant. We use the same way. Consider the shells, we break the shells into rings. And so as you can see, this is an interesting equation because in this equation, instead of having little r, which is a variable, in the denominator, we have a capital R. That's the radius of shell. The radius shell is constant. That means U doesn't depend on r, the little r. So, and thus have the same value everywhere inside the shell. So when m moves around inside the shell, that means when little r changes, U doesn't change. If the U is not changing, that means there is no force. Remember, force is derivative of U. So if U is constant, that means force has to be zero. So that means when m is inside any spherically symmetrical mass distribution, the gravitational force on mass is the same as though we removed all the outer layers. All the outer layer mass is removed. So only the inside, whatever inside counts. Test your understanding. In a classic novel, At Earth's Core by Edgar Rice Burroughs, explorers discovered the Earth is a hollow sphere and that an entire civilization lives on the inside of a sphere. Would it be possible to stand and walk on the inner surface of the hollow, non-rotating planet? The answer is no. We just saw that in a hollow sphere, there is no gravitational force inside the sphere. So you can't possibly to stand or walk without gravity. Apparent weight and Earth rotation. Because the Earth rotates on its axis, it is not precisely an inertial frame of reference. For this reason, the apparent weight W of the body on Earth is not precisely equal to the Earth's gravitational attraction, which we call the true weight, W naught of the body. So W naught is G MEM over RE squared. So what is apparent weight? Apparent weight is when you stand on the scale, then you see your weight. That's apparent weight. So what happens when an object is pulled by a spring scale? Say if you want to measure weight, you use the spring scale, right? So there are two forces acting on the object, F and W naught. So where F is the apparent weight, but in the opposite direction as apparent weight. The vector sum of F and W naught is the centripetal force because that is the net force required to rotate the object around Earth's axis. So F plus W naught vector addition equals to mass times centripetal acceleration. And F and negative W, F equals to negative W, that means negative W plus W naught equals ma rad. We can solve for apparent weight actually equals to W naught minus m times centripetal acceleration. So this gives us the apparent G and true G. So apparent G equals to true G minus centripetal acceleration. At North Pole, A rad equals to 0 there because at the pole you are not rotating. That means G equals to G naught, W equals to W naught. Only at poles, apparent weight is the same as true weight. As you move from the pole, your apparent weight is getting less and less. At the equator, you'll have the least value. That is because A rad is the biggest. So the body has smallest weight at the equator compared to the other positions around Earth. The difference between G naught, the true value, and apparent G is 0.0339 meters per second squared. So at the North Pole, your G value is the same as G naught, but at the equator, your G value is 9.8 minus 0.0339. Apparent weight and apparent weightlessness. So apparent weight equals true weight minus centripetal force. So equals to mg naught minus ma rad. For a spacecraft in orbit as well as anybody inside a spacecraft, the acceleration a rad equals to g naught. That means your apparent weight equals to 0. This is what we mean when we say that an astronaut or other body in the spacecraft is apparently weightless. Test your understanding. Imagine a planet has the same mass and radius as the Earth, but that makes 10 rotations during the time the Earth makes 1 rotation. What would be the difference between acceleration due to gravity at a planet's equator and acceleration due to gravity at its pole? So let's see. The difference we said is equals to A rad, and A rad equals V squared over R. Since V increased by 10 times, that means A has to increase by 100 times. Therefore, we already know on Earth the difference is 0.0339. So on the planet, the answer, I forgot another 3 here, right? It should be 0.0339. So the answer should be D. Now let's talk about escape speed. So our sun with a mass m about 2 times 10 to the 30 kilograms and radius about 7 times 10 to the 8 meters is much bigger than any planets. But compared to other stars, it is only medium size. We can find the sun's density by using m divided by v, which give you 1,410 kilograms per meter cubed. The sun contains no solid liquid due to its high temperature, yet the gravitational pulls on sun's gas atoms together until its density is 41% more than the water and 1,200 times as dense as the air we breathe. So it's very dense compared to the Earth and the water. Escape speed at the surface of the sun, using the escape equation, we can get 6.18 times 10 to the 5 meters per second. So the second equation, how do we get this? We use the m equals to the density times the volume. That's how we get this. So we know this escape speed does not depend on the mass of the escaping body. It only depends on the mass and the radius or the average density and radius of the sun. So this equation tells us for a given value rho, the escape speed is directly related to r. So from this equation, John Mitchell, who was an amateur astronomer in 1783, he noted that if a body has the same density as the sun, but with 500 times the sun's radius, then what that means, the escape speed would be greater than the speed of light, c. That means all light emitted from such a body would be made to return toward it. Mitchell was the first person suggested that the existence of what now we call a black hole, an object exerts a gravitational force on other objects but cannot emit any light of its own. So that was in 1783. So he thought something like that could exist. So this equation actually suggests, the escape speed suggests that a body of mass m will act as a black hole if its radius r is less than or equal to a certain critical radius. So in 1916, Carl Schwarzschild used Einstein's general theory of relativity to derive an expression for critical radius Rs. Now we call this critical radius Schwarzschild radius. Rs equals 2g times m over c squared. So this is critical radius. What does this significance of this equation tell us? It tells us that if a spherical non-rotating body with a mass m has a radius less than this Schwarzschild radius, that means nothing, not even light, can escape from the surface of this body. This body is a black hole. In this case, any other body within a distance Rs of the center of the black hole is trapped by gravitational attraction of the black hole and cannot escape from it. So the surface of this sphere is called the event horizon. Since we can't see events occurring inside, all that an observer outside the event horizon can know is its mass, its charge, and its angular momentum. We can figure out its mass to see how other bodies rotating around it. We can find its charge by how, again, its interaction with other charged objects. We can determine its angular momentum by examining how the space around it, because the black hole drags space around it and other objects around it. So let's take a look at this example, black hole calculations. Astrophysical theory suggests that a burnout star will collapse under its own gravity to form a black hole when its mass is at least 3 solar masses. If it does, what is the radius of the event horizon? So what's the radius? Let's see, the mass is 3 times of sun's mass, so it's about 6 times 10 to the 30. So we already know that the radius of event horizon is Rs. So that gives us 8.9 kilometers. Let's take a look at the density of this star, collapsing star. The density would be 2 times 10 to the 18 kilograms per meter cubed. The radius actually is very small. It's less than 6 miles, the density. And the density is as great as the density 10 to the 15 times as great as the density of familiar matter on Earth. The density of atomic nuclei. In fact, once a body collapses to a radius Rs, nothing can prevent it from collapsing further. All of the mass end up being crushed down to a single point. We call that singularity. Maybe you will hear that again at the center of the event horizon. This point actually has 0 volume and has infinite density. A visit to black hole. I'm running out of time, so I want you to rate this. So this is your point of view and your friend's point of view. It's 2 drastically different versions. And here is how do we detect black holes. We can detect black holes through the object around it. And also we can detect by analyzing orbits of the other stars around it. So there's 2 different ways. Okay, last one, check your understanding. what is your, would it shrink, would it expand, would it not change? The answer is it wouldn't change. Okay, that's it for today. Thanks.